Welcome to Dawn. Don't forget to subscribe. Imagine a pillar of fire 300 feet tall, a roaring orange beacon visible from the shores of Louisiana, erupting from the heart of the Gulf of Mexico. It is April 20th, 2010 at approximately 9:45 p.m. On the deck of the Deepwater Horizon, a $560 million marvel of modern engineering, the world is literally exploding. This wasn't a slow leak or a localized fire. This was a catastrophic blowout, a geyser of methane gas and drilling mud shooting up from 18,000 feet below the Earth's crust with the force of a volcanic eruption. The sheer kinetic energy of the blast was so intense it buckled steel plating and shattered reinforced glass windows instantly. One moment the crew was winding down their shift, some celebrating 7 years of operation without a single lost time accident, the next they were running for their lives through a maze of twisting metal and choking smoke. But here is the most chilling detail we will uncover today. 40 minutes before the first spark ignited the air, the rig's own sensors were screaming that a disaster was imminent. The data logs showed a massive pressure spike that shouldn't have been there. The computers knew the well was kicking. Yet in a display of fatal optimism, the decision makers on board looked at the evidence and convinced themselves it was just a technical glitch. We are going to deconstruct the anatomy of this failure, exploring how a rig that had won multiple safety awards became a graveyard in the span of seconds. By the end of this video, you will see how a series of successful pressure tests were actually the blueprint for a tomb. To understand why this happened, we first have to understand the sheer scale of the Deepwater Horizon. This wasn't just a boat, it was a fifth-generation, ultra-deepwater, dynamically positioned semi-submersible offshore drilling rig. To put that in perspective, the deck was the size of 2 professional football fields stitched together. It stood about 330 feet tall from the waterline to the top of the derrick, roughly the height of a 30-story skyscraper floating in the middle of the ocean. It weighed more than 32,000 tons. If you took the Eiffel Tower and multiplied its weight by 4, you would still be thousands of tons short of the mass of this floating titan. The rig was designed to operate in water up to 8,000 feet deep and could drill holes into the Earth's crust nearly 6 miles deep. That is the equivalent of standing on the peak of Mount Everest and drilling a hole all the way down to sea level, all while floating on a restless, moving ocean. It was a masterpiece of human ambition owned by Transocean and leased by the global energy giant BP. At the heart of the operation was the Macondo well, located in the Mississippi Canyon Block 252. The water depth here was approximately 5,000 feet. That is nearly a mile of vertical water column, the height of 5 Empire State Buildings stacked on top of each other. At that depth, the pressure of the ocean water alone is roughly 2,200 pounds per square inch. Imagine a fully grown African elephant standing on a single postage stamp. That is the kind of crushing, relentless force the equipment had to withstand before even touching the seafloor. Beneath that floor, the drill bit had traveled another 13,000 feet through rock and silt to reach the oil reservoir. The total depth of the well was 18,360 feet. To manage this, the rig used a riser, a massive steel pipe that connected the rig to the wellhead on the ocean floor. This riser acted as a high-pressure umbilical cord, carrying drilling mud down and bringing oil and debris up. The most critical piece of safety equipment was the blowout preventer, or BOP. This was a 450-ton stack of hydraulic valves and shears sitting on the seabed. It was 5 stories tall. Imagine a 5-story apartment building made of solid high-tensile steel designed for one specific purpose: to pinch a pipe shut in an emergency. It was supposed to be the God switch. If the pressure from the earth became uncontrollable, the crew could hit a button and the BOP would fire massive rams that would sever the drill pipe and seal the well forever. It even had a failsafe called the deadman switch. If the rig lost power or communication, the BOP was supposed to fire automatically. It was the ultimate insurance policy. Everyone believed it was invincible. Shattering the assumptions of safety is the core of this tragedy. The Deepwater Horizon was not a rust bucket or a neglected asset. It was an elite, state-of-the-art vessel. It held the world record for the deepest oil well ever drilled. It had been inspected and certified by the US Coast Guard. Only weeks before the explosion, it had undergone a rigorous audit. In 2008 and 2009, the Minerals Management Service had even nominated the rig for Safety Awards for Excellence. Every sensor was calibrated, every protocol was documented, and the crew was composed of the best engineers in the business. Yet, all that paperwork and all those certifications created a dangerous illusion of safety. They believed so much in their technical superiority that they began to interpret warning signs as anomalies rather than threats. As we move into the mechanics of the catastrophe, you'll see how a single decision to save a few hours of time led to a chain reaction that no machine on Earth could stop. This wasn't a failure of technology, it was a failure of the humans who thought they had mastered it. The disaster at the Macondo well didn't happen because of a single catastrophic explosion. It was the result of a death by 1,000 cuts, a series of engineering compromises driven by a project that was 43 days behind schedule and over $50 million over budget. To understand the physics, you have to look at the well as a pressurized soda bottle 5 miles deep, where the only thing keeping the cap on was the weight of the drilling mud. In offshore drilling, we use a concept called hydrostatic pressure. Think of it like this. If you dive to the bottom of a pool, you feel the weight of the water pushing on your ears. Now imagine a column of heavy synthetic mud 5 miles high. That mud exerts a massive downward force or hydrostatic head, which is designed to be greater than the pressure of the oil and gas trying to push upward from the reservoir. This is the primary barrier. If the mud is too light, the earth wins. If it's too heavy, it cracks the rock formation and you lose your lid entirely. On the Deepwater Horizon, the engineers were walking a razor-thin tightrope between these two extremes. The first domino to fall involved the cement job. In the world of deep-sea engineering, cement isn't just glue, it's a high-tech structural seal. Its load capacity must be sufficient to withstand the incredible tectonic forces of the Earth while preventing gas from leaking up the outside of the pipe, a space known as the annulus. To save time, BP chose a long string casing design rather than a liner design. A liner would have provided more layers of protection, but a long string was faster. To make the cement lighter so it wouldn't crush the fragile rock at the bottom, they injected it with nitrogen gas. This created a foamed cement slurry. Imagine trying to seal a high-pressure steam pipe with shaving cream instead of solid mortar. If that foam doesn't set perfectly, it becomes porous, allowing gas to channel through it. To make matters worse, the crew only used 6 centralizers, devices meant to keep the pipe in the middle of the hole, instead of the recommended 21. Because the pipe wasn't centered, the cement flowed unevenly, leaving a thin, weak spot on one side. This created a yield strength failure point where the pressure from the reservoir could eventually punch through. By the afternoon of April 20th, the well was sealed with this questionable cement, and the crew began the negative pressure test. This is a critical safety check where you bleed off the pressure inside the pipe to see if the well remains stable. It's like sucking the air out of a straw and putting your finger over the end to see if the liquid stays down. If the pressure rises when you close the valve, it means the well is leaking. During the test on the Deepwater Horizon, the drill pipe pressure jumped to 1,400 pounds per square inch. In any other scenario, this would be an immediate stop work order. It was a screaming warning that the cement had failed. But the supervisors on board were so focused on finishing the job that they convinced themselves of a physical impossibility. They claimed that the pressure reading was a bladder effect, a temporary anomaly caused by the heavy mud pushing on the internal components of the wellhead. They ignored the laws of physics to satisfy a schedule. They decided to run the test again on a different line which showed zero pressure, and they called it a success. They had effectively convinced themselves that the straw was sealed when it was actually wide open to a reservoir of high-pressure methane. The point of no return came during the mud to seawater displacement. To finalize the well, they had to pump out the heavy drilling mud and replace it with much lighter seawater. This was the moment the hydrostatic lid was removed. As the heavy mud was pumped out, the hydrostatic head dropped. The gas in the reservoir, previously held back by thousands of tons of mud, finally found its opening. It began to seep through the channeled nitrogen cement and into the casing. This is what engineers call a kick, but because the crew was busy with other tasks, they didn't notice the flow sensors for nearly 40 minutes. Inside the pipe, the methane gas was beginning a violent ascent. Methane follows Boyle's law. As the pressure decreases as it rises toward the surface, the volume of the gas expands exponentially. By the time that gas reached the top of the well, it had expanded by more than 1,000 times its original volume. It wasn't just a leak anymore, it was a deep water elevator of pure explosive energy, traveling at supersonic speeds up the riser toward the rig. At 9:40 p.m., the first surge of mud and gas erupted onto the deck. The load-bearing structure of the well was gone. The gas bypassed the diverter system and was sucked into the rig's massive diesel engines. In a diesel engine, you control the speed by controlling the fuel. But when the engine started breathing methane-rich air, it had an unlimited fuel source. The engines began to run away, spinning faster and faster until they reached their mechanical yield strength and shattered. Metal fragments flew like shrapnel, sparks ignited the gas cloud that had enveloped the rig, and the Deepwater Horizon was transformed from a miracle of engineering into a multi-story furnace. The bridge lost all angle of inclination control as the dynamic positioning system failed, and the rig began to drift, still tethered to the erupting volcano of fire below. There was no wind load calculation or safety factor that could account for the sheer volume of fuel now feeding the inferno. The sound was the first thing that signaled the end. Survivors described it not as a bang, but as a low-frequency vibration that rattled their very marrow, like 1,000 freight trains screaming through a tunnel. At 9:45 p.m., a geyser of mud, gas and water shot 240 feet into the air, drenching the derrick. On the bridge, dynamic positioning operator Yancey Keith saw the gas-high alarms light up the console like a Christmas tree. Within 10 seconds, the methane had found its way to the engine room. When the massive diesel generators inhaled the gas, they didn't just speed up, they tore themselves apart. The first explosion was a muffled thud from deep within the rig's hull. The second, just 10 seconds later, was a concussive blast that ripped through the living quarters. The force was so immense it blew heavy fire doors off their hinges and threw men from their bunks across the room. In those first 60 seconds, the rig became a vertical labyrinth of fire. 11 men were killed almost instantly, most of them standing on the drill floor or near the engines where the blast was most concentrated. We remember names like Jason Anderson, a senior tool pusher who was a father of two, Dewey Rivette, a driller with 29 years of experience, and Donald Clark, who was planning to retire soon. These weren't just personnel, they were the elite of the offshore world. For the 115 survivors, the next minutes were a desperate scramble for life. The emergency lighting failed, leaving the corridors in pitch-black darkness filled with the smell of burning rubber and scorched metal. Some crew members, unable to reach the lifeboats due to the heat, were forced to jump from the deck, a 75-foot drop into the oil-slicked, burning waters of the Gulf. That is like jumping off the roof of a 7-story building into a dark churning abyss. While the crew fought to evacuate, the gut switch, the blowout preventer on the seafloor, failed its one and only job. When the bridge crew tried to activate the emergency disconnect system, nothing happened. Later investigations revealed a nightmare of technical negligence. The deadman switch, designed to trigger if the rig lost power, had a low battery and a faulty solenoid valve. Even if it had fired, the blind shear ramps, the heavy steel blades meant to cut the pipe, would have likely failed. The drill pipe inside the BOP had buckled due to the extreme pressure moving out of the center. It's like trying to cut a piece of paper with a pair of scissors when the paper is folded into a thick, jagged wedge. The blades simply couldn't meet. The well remained wide open, a high-pressure artery of the earth pumping 50,000 barrels of oil a day directly into the ocean. The immediate response was a chaotic fleet of fireboats and Coast Guard vessels. For 36 hours they pumped millions of gallons of water onto the Deepwater Horizon, but it was like trying to put out a forest fire with a garden hose. The heat was so intense it began to melt the rig's aluminum structures. On April 22, 2010, the Titan finally lost its buoyancy. The rig tilted, groaned and slipped beneath the waves, dragging the massive riser pipe down with it. As it sank 5,000 feet to the bottom, it kinked the pipe, creating the broken straw image that would haunt news cycles for the next 87 days. The aftermath was a legal and scientific firestorm. The investigation involved thousands of pages of data logs and recovered black box records. The blame game between BP, Transocean and Halliburton was a masterclass in corporate finger-pointing. BP was the operator, Transocean owned the rig, and Halliburton did the cement. The US government's investigation, led by the Marine Board of Investigation, found that the disaster was preventable. It wasn't an act of God or an unpredictable freak accident. It was the result of a management culture that prioritized speed over safety. In 2014, a federal judge ruled that BP was grossly negligent and bore the lion's share of the blame. The company was hit with over $65 billion in cleanup costs, fines, and settlements. This was the most expensive industrial accident in human history. To visualize that, $65 billion is enough to buy every single person in the city of New York a brand new high-end car. But the financial cost paled in comparison to the environmental and human toll, leading to a total restructuring of how we police the deep. The oil did not stop flowing when the rig sank. It was only the beginning of an 87-day environmental siege. By the time the Macondo well was finally capped on July 15, 2010, an estimated 134 million gallons of oil had spewed into the Gulf of Mexico. To visualize that, imagine a line of standard oil barrels stretching from New York City to London and back again, twice. The spill covered an area of 68,000 square miles, roughly the size of the entire state of Oklahoma. This wasn't just a localized accident, it was a planetary-scale trauma that exposed the terrifying reality that we had the technology to drill into the heart of the Earth, but no proven technology to stop the Earth from bleeding if something went wrong. The desperate attempts to kill the well, the top kill where they tried to pump heavy mud into the wellhead, and the junk shot where they literally fired shredded tires and golf balls into the pipe to clog it, were engineering improvisations that felt more like 19th century blacksmithing than 21st century science. The fallout triggered a total seismic shift in how the world regulates offshore energy. Before the disaster, the industry was governed by the Minerals Management Service, or MMS. This agency was a textbook definition of a conflict of interest. They were responsible for collecting billions of dollars in oil lease revenues for the government while simultaneously enforcing safety regulations. It was like having a casino owner also act as the head of the gaming commission. The incentive was always to keep the games running. In the wake of the fire, the MMS was abolished. In its place, the US created the Bureau of Safety and Environmental Enforcement, BSEE. For the first time, the people collecting the money were not the same people inspecting the rigs. This reform introduced the well control rule, a massive set of standards that mandated more robust load capacity for blowout preventers and required real-time onshore monitoring of deepwater drilling data. Today, every move a rig makes in the Gulf is watched by engineers in high-tech mission control centers on land hundreds of miles away. But perhaps the most shocking revelation of the investigation was that this had all happened before. In June 1979, a well called Ixtoc 1 suffered a blowout in the Bay of Campeche, Mexico. The causes were almost hauntingly identical: a failed cement job, ignored pressure warnings, and a blowout preventer that couldn't shear the pipe. The Ixtoc spill lasted for nearly a year and was, until 2010, the largest accidental spill in history. The engineering community had the blueprint for the Deepwater Horizon disaster 30 years before it occurred. We were warned by history, yet we allowed normalization of deviance, the dangerous habit of seeing small errors as acceptable, to blind us. We built bigger rigs and drilled deeper holes, but our safety mindset stayed stuck in the shallow water of the past. The industry had developed metal fatigue not just in its pipes, but in its ethics. Today, the most significant technical legacy of the disaster is the capping stack. Before 2010, the industry had no lid ready to go. Now, companies like the Marine Well Containment Company maintain massive 100-ton steel capping stacks in a state of constant readiness. These are the fire extinguishers of the deep sea. If a blowout occurs tomorrow, a fleet of ships is contractually obligated to deploy these stacks within days, not months. It is a multi-billion-dollar insurance policy written in the ink of crude oil and human life. We have finally accepted that unlikely is not the same as impossible. Philosophically, the Deepwater Horizon is more than just a failure of yield strength or seismic load calculations. It is a mirror of systemic human ambition. We live in a world that demands cheap, constant energy to fuel our cities, our cars, and our digital lives. Yet we rarely look at the jagged edges of the frontier where that energy is won. The disaster was a reminder that when we push the limits of physics in environments as hostile as the deep ocean, the safety factor must be more than a number in a manual. It must be a culture that is willing to stop the clock even when millions of dollars are on the line. The 11 men who died that night were the vanguard of our energy-hungry civilization, and their sacrifice forced us to realize that the true cost of oil isn't paid at the pump, it's paid in the dark, 5 miles below the surface. What do you think? Should we continue to push even deeper into the Earth's crust, or has the Deepwater Horizon shown us a limit that we simply aren't ready to cross? Let me know your thoughts in the comments below. If you found this deep dive into engineering history valuable, hit that like button and subscribe to stay updated on our latest investigations into the world's most complex megaprojects and disasters. Thanks for watching, and stay curious.